The past 5 years have been the Earth's warmest years on record. Global sea levels have risen 8 inches in the last century, and Antarctica has lost almost 3 trillion tons of ice over the last 30 years. These trends are all indicative of long-term global warming due to human activities such as burning fossil fuels for energy and transportation, something every single one of us contributes to every time we take our car to work or to the store. Good afternoon. My name is Anna Stevenson. I'm a junior at the University of Alabama, majoring in mechanical engineering. And this past semester, I conducted research with Dr. Agarwal and Dr. Biddle in the mechanical engineering department on characterizing properties of fuels for use in low-emission diesel engines. The goal of our project, which is done in partnership with the Department of Energy, is to accelerate the deployment of co-optimized fuels and engines that will improve fuel efficiency while also reducing soot and greenhouse gas emissions. Since too much greenhouse gas and soot in the atmosphere can lead to excess heat being trapped in the atmosphere, this causes the planet to warm more rapidly than necessary, which is dangerous when done at an uncontrolled rate. By working to reduce emissions and soot, we can work to slow some of the harmful effects of the greenhouse gas effect. Additionally, current diesel engines require expensive after-treatment systems in order to meet strict emissions regulations. So by working to reduce emissions, we can work to reduce the need for these types of systems. Our project is supported nationally at several different labs and universities, including here at UA, where our individual work focuses on developing models to predict combustion characteristics for different fuels as they combust in an engine-like environment. There are two parameters that are typically used in order to describe combustion behavior, which I will briefly define here before going into more detail about later. The first is liftoff length, which is defined as the distance between where fuel is injected and where signal shows up closest to the fuel injector. And the second is ignition delay, which is defined as the time between start of injection, or SOI, and when ignition actually begins. In order to collect data to analyze these different fuels, we use a constant pressure flow rig, or a CPFR. Fuel is injected into this chamber, which is able to simulate ambient conditions of temperatures up to 1000 Kelvin and pressures up to 50 bar. This chamber is able to maintain highly repeatable, nominally constant test conditions, and we're able to obtain large data sets on the order of 360 fuel injections per hour, which allows us to collect large, statistically significant data sets and then analyze them. The chamber also allows for line-of-sight optical access, and we utilize 3 different types of optical diagnostics in order to study fuel injection reaction behavior. This is an aerial schematic of the system we use in our lab to analyze fuel injection, ignition, and combustion behavior inside of the constant pressure flow rig, which is shown here. The first is a rainbow Schlieren deflectometry camera, or RSD camera, which is shown here, which quantifies how the fuel mixes with the air. The second is a 2-color pyrometry camera, which characterizes soot formation. And the third is an OH chemiluminescence camera, which characterizes the formation of the flame inside of the chamber. This is a high-speed video of the fuel injection, ignition, and subsequent combustion processes inside of the spray chamber. The injection lasts approximately 2 milliseconds before igniting downstream. It's important to note that this video has been rotated 90 degrees for viewability, and that in actuality, the fuel would be injected and propagate downward. This is another video that shows the simultaneous playback of 3 different optical diagnostics we use to study the flame injection, ignition, and combustion. On the left, you'll see the chemi camera. In the middle, you'll see the RSD camera. And all the way on the right, you'll see 2-color pyrometry. Again, the chemi camera shows us flame structure. The RSD camera shows us how the fuel is mixing with the air. And the 2-color pyrometry camera shows us where the soot is forming inside of the flow rig. When you see bright spots show up in the middle of the chemi and the 2-color pyrometry frames, as well as a yellow spot show up at the bottom of the RSD frame, that indicates that ignition has begun. My role in this project has dealt primarily with analyzing data from the chemiluminescence camera. The chemi camera provides us with qualitative information about the structure of the flame. The chemi camera picks up signal once ignition begins. So before ignition begins, there's no signal and the image is simply black. Once chemical reactions excite OH, the camera starts to pick up the signal, so you start to see a bright spot. And then as the flame propagates throughout the chamber, the signal becomes most dominant where the flame stabilizes downstream. I was tasked with using the chemiluminescence data in order to quantify liftoff length and ignition delay for N-heptane fuel, as well as 2 fuel blends, N-heptane blended with 10% butyl acetate and N-heptane blended with 20% butyl acetate. Again, ignition delay is defined as the time between when fuel is injected and when ignition begins. And liftoff length is defined as the distance between the fuel injector and the closest signal, shown in this image by the red arrow. The chemi data can be transformed using a mathematical process known as Abel inversion. This image shows the raw chemi data in the top row and the inverted chemi data in the bottom row. The Abel transform can essentially be used to calculate a radial mass distribution and allows us to take a 2D slice of a 3D flame. The Abel transform reveals that a majority of the key reaction zones are occurring around the edges of the flame as opposed to the center, which is what the raw data might appear to indicate. Boundaries can be detected using this inverted data and overlaid on the raw data, again highlighting that the key reaction zones are occurring around the perimeter of the flame as opposed to the center of the flame. If you imagine taking those boundaries and rotating them, you would see that the key reactions are occurring around the edges. These boundaries can be tracked throughout time, and they can also be detected fairly well, although sometimes they are affected by the presence of background noise, which moving forward we are working to mitigate. The boundaries can be used, as I said, to track 3 key points throughout time for each injection. On the left, the centroid is being tracked. In the middle, the liftoff length and reaction head, essentially the extreme maximum and minimum of the boundaries are being tracked. And on the right, the location of maximum intensity is being tracked. Each image has been broken up into 4 quadrants, left, right, near, and far, and these key points are tracked throughout time for each of the 4 quadrants. These key points can then be plotted throughout time, and this plot here shows the key location plots for 25 injections of N-heptane fuel. The solid lines represent the average of each key location, and the dotted lines indicate the standard deviation of each key location. These same plots can be generated for the fuel blends as well in order to understand the differences between how each fuel blend reacts inside of the chamber. Here, similar plots have been generated comparing the 10 and 20% butyl acetate fuel blends to the N-heptane case. The N-heptane case is still being shown in blue and black, while the fuel blends are being shown in red and green. On the left, the 10% case is being compared against N-heptane, and on the right, the 20% case is being compared against N-heptane. And only the averages are being shown here, as opposed to the averages and the standard deviation, just for simplicity. We can use these plots in order to study the differences between the fuel blends, notably ignition delay, the time until signal shows up, shown by this red arrow, as well as stable liftoff length, which we define as the average liftoff length from 3.5 to 5 milliseconds, highlighted by this red box. The average stable liftoff length and average ignition delay can be plotted as a function of percent butyl acetate. Here, the error bars represent standard deviation. As you can see in the left plot, the stable liftoff length increases with percent butyl acetate, which is the trend that we expected to see. However, for ignition delay, you'll see that while ignition delay does increase for the 10% case, it decreases for the 20% case, while we would again expect ignition delay to continue to increase as the percent of butyl acetate increases. There are a couple reasons why this trend might be appearing this way. You'll notice the large error bars, the large standard deviation, which indicates is probably a factor contributing to the decrease in ignition delay. Additionally, as I mentioned before, the program for boundary detection does struggle a bit at picking up the initial signal during at the start of ignition because of the background noise, which also might have had an impact on this trend as well. And moving forward, we will be analyzing more injections in order to gain a more comprehensive understanding of both of these trends. So in the future, the goal of this project is to continue performing experiments in the chamber with different fuels and fuel blends and to explore the relationships between each type of fuel and how it combusts inside of the chamber. Ultimately, the goal is to be able to compile comprehensive combustion characteristic indicators and develop models to predict which fuels and fuel blends will be the most efficient and the least emissive. Ultimately, determining which type of fuels make the most sense for public use will allow us to, as a society, combat the growing climate crisis and ultimately reduce our overall need for fossil fuels and reduce our total greenhouse gas emissions. Thank you, and are there any questions?
Anna, can you go into a little bit more depth on how the rainbow Solarian and the two-color pyrometry diagnostics work and what they're used for?
Of course. So as far as the rainbow Schleyer deflectometry setup goes. This slide shows on the top typical RSD experimental setup. And so for an RSD setup, a color filter is used to measure the deflection of light rays as they pass through a test medium. And the filter that is used is a continuously graded rainbow filter, and it transmits light of a particular wavelength or color, essentially, corresponding to the location where the light hits it on the filter. So in the bottom image, for example, the red corresponds to minimal deflection, while the violet would correspond to maximum deflection. And then you can use this color coding scheme to essentially calculate axial displacement of light and correspond that to a location, pixel location in the Schleyer image, which I showed earlier during the simultaneous playback of the 3 diagnostics. And that displacement calculation allows us to quantify how much the fuel is essentially displacing and mixing with the air. On the other hand, the 2-color pyrometry system allows us to measure temperature based on thermal radiation of an object based on 2 different wavelengths. So this is our overall diagnostic setup, and this is the 2-color pyrometry setup being highlighted in the red box. The incoming soot radiation, which is shown by the blue arrow, is split by a beam splitter, and then 2 spatially identical images are filtered at 550 and 650 nanometers. And then the ratio of the radiation at those 2 wavelengths, it varies pretty proportionally with the temperature of the object. So you can map the pixels to different wavelengths and then use the ratio of the 2 wavelengths to calculate soot formation.
Why choose to research alternative fuels rather than alternatives to fuel in general?
If I understand your question correctly, fuels have, their diesel engines already have the capability to be made fairly efficient. But like I said before, they require expensive after treatment, and they're not always feasible to make work for applications like jets, which are incredibly heavy. And so moving forward, I think moving forward into the future, I think that fuel will be the more important component than necessarily just focusing on something like improving the engine, because there are already a lot of capabilities for improving engine performance out there. But I think moving forward, especially since fossil fuels are rapidly depleting, we will need to focus on a more sustainable way to fuel traditional engines as well as modified diesel engines.
Very good. And unfortunately, that's all the time we have. So great job, and thank you for your presentation.